Lecture 16, Message Ordering and Group Communication. Preface, recap of previous lecture. In previous lecture we have discussed about termination detection and set of representative termination detection algorithm based on the concept of snapshot collection, weight throwing and spanning tree. Content of this lecture. In this lecture we will discuss about message ordering, group communication and multicast, that is multicasting. Introduction. At the core of the distributed computing is the communication by message passing among the processes participating in the application. So in this lecture we will study several message ordering paradigms for communication such as asynchronous, synchronous, FIFO, causally order and non-FIFO order. These orders form the hierarchy. We will examine few algorithms to implement these orderings. Group communication is an important aspect of communication in a distributed system. Causal order and total order are popular forms of ordering when doing group, multicast and broadcasts. Algorithm to implement these orderings will also be discussed. Before we go ahead, let me give you few examples where this message ordering and multicasting will be useful. So as you know that in a distributed databases, the database is normally replicated to at more than one sites. Now whenever there is an update at the database, then at all places, that is at all the replicas have to be updated instantaneously. So if two messages are sent for update at different point of time, so this particular order in which two messages are sent, these updates are to be made in that same order irrespective of how much delay the messages are ensuring. How this is all done? This is all done here in ordering of messages. And also another form of message ordering or communication in a group is basically called multicasting. So multicasting is an example of two cases. One is called closed group and the other is called open group. Open group is like online railway reservation system where any customer at any point of time can come and enter into a system and perform the operations. So that client, an external person, is using a set of nodes for its application, then it is called an open system. Open system communication is basically done through the multicasting. So if large number of users are allowed in reservation systems, then it is not so easy task, it is a difficult task to basically ensure the correctness and running the application. So this will be talked about during the group communication and multicasting, how this paradigm is going to be implemented in the system of message passing system, that is called distributed system. There are a few notations and some of these notations are explained, so we skip this. Now message ordering paradigms. Message ordering paradigms, the order of messages in a distributed system is an important aspect of system executions because it determines the messaging behavior that can be expected by the distributed program. So distributed program logic greatly depends on this order of delivery. To simplify the task of a programming languages in conjunction with the middleware provides well-defined message delivery behavior. So again, reiterate on the same point, the message, the order of delivery of the message is most important as far as distributed applications are concerned, and it reflects and it depends and that particular ordering comes from the applications, and the implementations will be basically governed here using the message ordering paradigms. So the programmer can send the code for the programming logic with respect to this particular behavior. There are several ordering on the messages which are defined as non-FIFO, FIFO, causal order and synchronous order. Let us see a few definitions on these different kind of message orders. So asynchronous execution, you know that is an execution for which causality relation is a partial order that we are seeing. Another thing is called FIFO. In a first in first out executions is an asynchronous execution in which for all pairs sender and receiver and another pair of sender receiver. So if these sender and these receivers, they are happening within a system and there is an order between the sender, then there will be an order in the receiver also, because these senders and these receivers are happening within a particular process, and so within a process they are happening. So if this particular send is preceding over the other send, that is S prime, so their receive also requires this kind of precedence relation, and that is called FIFO if that is being preserved. So here the communication channel has to ensure that the delivery is to be following the FIFO manner. Similarly, the causal order is an execution in which for all senders and receivers, where these senders S and S prime, they are basically sending to the same destination, that is R. And if there is a precedence between the send operation, that means if S precedes S prime, then this particular receive process R also precedes R prime, and R prime is happening at the same process. That is what this particular symbol indicates. So the diagram reflects whatever is the definition of a causal order. So if there is a precedence between two sends which are happening at different sites, then when they will be received, and if they have a precedence relation, so that relation also will be ensured at the time of delivery, and that ordering of the message is called causal ordering of messages. Now another kind of ordering is called synchronous, that sync order. An execution for which the causality relation is a partial order is called the synchronous order. So synchronous order is like for every send there will be a instantaneous receive. So this will be handled as far as synchronous ordering is concerned over an asynchronous communication channel. So that means the sender and the receiver, they basically work in a synchronization, and whatever sender is sending, receiver will be receiving within that synchronization. They are called synchronous ordering. So it is also called the instantaneous communication, and this is the modified definition of causality. These kind of ordering, that is we have defined like non-FIFO order, FIFO order, causal and synchronous order, they basically follow an hierarchy in the execution class, which is shown over here in the figure at A. So in this particular figure you can see this kind of relation holds, where the causal order is a proper set of FIFO and synchronous is a proper set of the causal order, and A means non-FIFO, A means asynchronous. So asynchronous doesn't follow any order, and that is why it is non-FIFO. So here we can see from this particular hierarchy that that sync or asynchronous order is basically a proper set of causal order, and causal order is a proper set of FIFO, and FIFO is a proper set of non-FIFO or an asynchronous. The examples here we can see that if it is a sync, that means sender and receiver they works in synchronization, they can be represented by this particular arrows. Causal order, in a causal order we can see that if these two sends they are having the precedence relation, or this send is happened before the other send, then as far as when they receive, so this particular order is also ensured at the delivery time. Hence S1 sorry hence S precedes S prime at the delivery also. Why? Because here they are following the receive order. In FIFO we can see that the order in which these messages are sent, the same order is preserved at the time of delivery of these messages. Asynchronous doesn't follow any order, so the order at the time of sending these messages is not preserved at the time of delivery of the messages. So this will include a hierarchy of these kinds. Now underlying the asynchronous mode, where the message passing follows the delivery of the message having unpredictable delays. These particular ordering, how they are going to be ensured, we are going to see in the further slides how they are going to be implemented and used up. Now the group communication. Processes across distributed system cooperate to solve a joint task. Often they need to communicate with each other as a group, and therefore there needs to be support for the group communication. So example of such applications are, for example, if there is a railway reservation system, which comprises of several nodes, so the person outside can directly communicate to this set of system which represents the railway reservation system, which includes a bank and the railways and so on, and this particular system requires a group communication. Why? Because this particular client or a user has to communicate only to a set of processes, and this is called a group of processes, and this kind of communication is called a group communication. Group communications are to be supported by the applications. A message broadcast is sending of a message to all the members in a distributed system. The notion of a system can be confined only to those sites, processes participating in the joint application. Refining the notion of a broadcasting, there is a multicasting wherein the message is sent to a certain subset identified as a group of the processes in the system. So at the other extreme is the unicasting, which is familiar point-to-point message communication. Let me tell you that broadcasting means sending a message to all, is called broadcasting. If sending message not to all but to a subset, or to a group, then it is called basically a multicasting. Now if sending the message to another node, then it is point to point communication, and it is called a unicasting. Now network layer or the hardware assist the multicast cannot easily provide application specific semantics on message delivery order, adopt groups to dynamic membership, multicast to arbitrary process set at each send, provide multiple fault tolerance semantics. So these are basically the few things or a few properties which has to be implemented. Why? Because in the network layer this hardware assist multicast cannot be provided. So I told you that the closed group, that is the source, is a part of the group. So the source is also a part of the group to which they have to communicate, then it is called a closed group. And an open group means if the source is outside the group, then it is called the open group. So this particular example which will tell you about the application specific semantics on the message delivery order. For example, there are two processes, P1 and P2. They are causally related through this particular message M, which is shown over here, and there are three sites, R1, R2, R3, which basically will maintain the replicas. So if message M1 is multicast, this is a multicast to all R1, R2 and R3. After that, P2 multicast another message M2 for updates on these replicas. Then let us see the scenario what happens. Now you know that P1 is sent before P2, and this particular message M ensures the precedence relation between P1 and P2. So as far as R1 is concerned, R1 will receive P2 first and then P1. So it is not following this particular precedence relation, it is violating. R2 is concerned, R2 is receiving P1 first and then P2, R3 is also receiving. So this particular update as far as the B is concerned is not basically causal order, and also total order is also violated. Total order in the sense which I will explain later on. Total order meaning to say that each site will see same ordering. So here you see that here P2 followed by P1 is the order in which the requests are coming for the updates. As far as R2 is concerned, R2 will have another view, P1 followed by P2. So basically it is not having the total order as well. So causal order is also violated and total order is also violated. Another scenario which says that in all other sites P2 and then P1. So P2 is occurring first, then P1, violating causal order is violated here in this particular scenario. We will discuss all these things in great details in this part of the lecture. Raynal-Schiper-Toueg algorithm in 1991. Let us discuss this algorithm for the group communication. Intuitively it seems logical that message M should carry a log of all other messages or their identifiers sent causally before M's send event and sent to the same destination M. This log can then be examined to ensure whether it is safe to deliver the message. All the algorithms aim to reduce this log overhead and space and time overhead of maintaining log information at the processes. So using this algorithm, the ordering which is required in causal order or the total order can be ensured before the delivery. Now if the messages are arrived which are not following causal order, then they have to be buffered, and applied this particular Raynal-Schiper-Toueg algorithm before delivery, they have to be buffered and ordered the way they want to be delivered, and that is why each process carries the log, each message carries carries the log of other messages. So the message becomes heavy. Why? Because it contains all this information of ordering, and when this message reaches to a site, it will be buffered, and based on the information which is contained in the log, the destination will try to order the messages in the buffer itself, and then accordingly it will be delivered as per the order. So let us see this particular algorithm which ensures the delivery. This algorithm assumes the FIFO channels, and there are two properties, safety and liveness. Safety property is ensured here in 2A, that is deliver message M which is received at PI, where this particular condition ensures that all previously sent messages are to be delivered before this message will deliver, otherwise it will be stored in the buffer itself. Now this particular algorithm, you can see that it requires the message space in the form of a log and also the local space, because these data structures, array of sent, array of deliver, they are to be maintained. So basically different techniques we will see that how they are going to reduce it, so that the overhead gets reduced and the algorithm becomes efficient and affordable to be implemented. Now we are going to see the total order. Total order requires that all the messages received in the same order by the recipients of the messages is formally defined as for each pair of processes Pi and Pj, and for each pair of messages that are delivered to both the processes Pi and Pi, both the processes Pi is delivered Px before Mx before My, if and only if Pj is delivered Mx before My. So this is called total order. So this particular figure I have already explained that this does not satisfy the total order, but this is satisfying the total order. Why? Because every process will have the same view, and if every process is having same view of the message delivery, then it is called the total order. How the total ordering of the messages is implemented. So we are going to see the first algorithm, which is called a centralized algorithm for total ordering of messages. So if Pi want to multicast a message M to a group G, then it will send, the Pi will send to the group coordinator, and the group coordinator in turn will send it to the group of messages. So this is called coordinator, and hence it is called a centralized algorithm, meaning to say that considering these particular channels are FIFO, so the order in which all the messages are being received with the coordinator, and when the coordinator will send to the group members, the messages will be ordered because they are assumed as a FIFO. So assuming all the process broadcast messages, the centralized solution shows in this algorithm enforces the order in a system with a FIFO channels I explained you. Each process sends a message it wants to broadcast to a centralized process, which simply relays all the message it receives to every other process over FIFO channel in the group. So it is straightforward to see that the total order is satisfied. Why? Because the order in which the messages are given by the coordinator, the same order it will be delivered. Hence this particular, since it's a total order, it also satisfies the causal order. Why? Because we have seen in the hierarchy class of this model. Complexity of this algorithm is that each transmission takes 2 message hops and exactly n messages in the system of n processes. The drawback is the centralized system has a single point of failure, and also there will be congestion towards that. So, another algorithm is called three-phase algorithm. Three-phase algorithm also ensures the total order. So, if it is ensuring total order, that means causal order is also ensured as far as the hierarchy of these classes are concerned. So, a distributed algorithm that enforces total order and causal order for closed groups is given by three-phase algorithm. So, the three phases of the algorithms are first described from viewpoint of the sender and then from the viewpoint of receiver. So, this algorithm has two parts. One is the sender part of the algorithm, the other is the receiver part of the algorithm. So, first we will see the all three phases of the sender, and in the receiver also we will see those corresponding three phases to the sender. So, sender phase 1, in the first phase a process multicasts, which is given in line number 1 of the algorithm that we will see, multicast message M with a locally unique tag and a local timestamp to the group members. Phase 2, in the second phase the sender process awaits a reply from all the group member who respond with their tentative proposal for a revised timestamp for that message M. The await call in line 1D is non-blocking, that is, any other messages received in a meanwhile are processed. Once all expected replies are received, the process computes the maximum of the proposed timestamp for M and uses maximum as the final timestamp. Third phase says that in the third phase the process multicasts the final timestamp to the groups in the line 1F. So, the sender will send 3 times. In the first phase 1 it will send the message 1 with a timestamp. Second time it will send, the sender awaits the reply from all, then it will send a tentative proposal for the revised timestamp. And third time it will send the messages with a final timestamp. And on the other side receiver will receive them and process them and replies them in all three phases that we are going to see here. So, in phase 1 the receiver receives the message with a tentative proposal timestamp which is sent by the sender. It updates the variable priority that tracks the highest proposed timestamp and then revises the proposed timestamp to the priority and places the message on its tag and revise the timestamp at the tail of the queue. In the queue the entry is marked as undeliverable. So, meaning to say that after receiving the messages from the sender, it basically finalize a tentative proposal timestamp, and accordingly the messages are placed in the queues and they are marked as undeliverable. They will not be delivered. Why? Because they are stored in the queue and according to timestamp they will be ordered and then delivered. So, to do that it will go for a second phase. The receiver sends the revised timestamp back to the sender. The receiver then waits in a non-blocking manner for the final. In phase 3 the final timestamp is received from the multicaster or from the sender. The corresponding message entry in a queue is identified using the tag and marked as deliverable after the revised timestamp is overwritten by the final timestamp. The queue is then restored using timestamp field of the entries. So, as the queue is already sorted except for the modified entry for the message under construction, that entry has to be placed into a sorted position. If the message entry is at the head of the queue, that entry and all the corresponding subsequent entries are also marked as deliverables, are dequeued from the queue and deliver to that particular process. So, this particular code I have already explained, and let us go through the illustrative example for the working or the execution of that three-phase algorithm. Now, here you can see that site A and site B, they want to send a message to those two replicas C and D. So, A will send with a tag 7 the message to D, and B will send with a tag 9 to C. Now D, when it receives this particular message with a tag 7, it will give its own timestamp and position it in the queue, that is called temporary queue. It will not be delivered. And similarly, first message, D will receive the first message from B, so it will be queued with that timestamp, and the next message 7, when it delivered, so timestamp will be incremented and will be given to this particular message a time 10. So on the head of the queue will be the message which comes from B. It will not be delivered, it will be just queued. This particular timing, which is basically the revised time or a proposed time, will be sent back from A to B in the second phase. Similarly, the 9 tag or a timestamp 9 is sent from D to B. Similarly, here 7 will be received first, so it will be enqueued on the top of the queue, and 7 will be returned back to A, and once 9 will be received, so 9 will be in the order, so 9 stamp will be returned back. Now it will process them. After receiving these values as 7 and 10, it will take the maximum over here, and this will be the final value, and A will send the final value 10 to both of them. Similarly, here after receiving 7 and 9 two values, the maximum is 9, and 9 will be sent back to both of them. So if you see here in this scenario, 9 is at the head of the queue, so from temporary it will be put on the delivery of the queue, and this message will be delivered to the process. Here also the same ordering will be done. Since 9 is at the head of the queue, it will be put on the delivery and 9 will be delivered. So first 9 will be delivered at both the ends, and then 10 will be delivered, so hence it follows the total order according to the algorithm. So all these steps of the algorithms are basically, I have explained you through the example. The complexity of this algorithm, since it uses 3 phases, in every phase a message is being exchanged, so in every phase n-1 messages are exchanged, so out of 3 phases 3 n-1 messages will be exchanged. Delay will be 3 message hop, because 3 times message will go and come back, so it will be 3 message hop delay will be there. It also implements causal order that we have already seen. So 3-phase algorithm is closely structured along the lines of Lampert's clock for the mutual exclusion. That algorithm we have studied. So Lampert's mutual exclusion algorithm has the property that when a process is at the head of its own queue and has received a reply from all the process request of that process is the head of all the queues, this can be exploited to deliver the message by all the process in the same order instead of entering into a critical section. So exactly on the same lines this particular algorithm was designed and structured. So we have seen the algorithm for total order, and that will be achieved through the algorithm. Why? Because underlying network is an asynchronous network which we are now assuming. So the ordering which is required from the application is to be ensured through that algorithm which we have just covered. Now the next topic is about the multicasting. So as I told you that unicasting, multicasting and broadcasting, there are 3 different ways of communication for the applications in a distributed system which is being utilized. So now we are talking about the multicasting, that is the communication to a group of processes. So 4 classes of source destination relations for the open groups are there. So that previous algorithm was for closed group. Here this example is basically, or this particular nomenclature is for the open groups. So the first nomenclature for the open group is triple SG, that is single source and single destination group, where there is a single source and the single group is for the destination, that is called triple SG. MSSG is basically multiple sources. Here you see there are multiple sources and a single destination called multiple sources single destination, MSSG. Then comes triple SMG, means single source and multiple groups. So here these multiple groups are overlapping also. And then MSMG, that is multiple sources. Here you see two sources are there and multiple groups which are overlapping also. So there are 4 different ways in which these open groups can be organized or can be classified. Now we can see that before we go ahead, let us see that it is quite easy to implement triple SPY, because this can be done using the centralized approach. So this will be a coordinator. For example, this will send to a coordinator and coordinator will basically sequence the messages in the order. So this is quite trivial. This also can be handled using the centralized approach, and MSSG can also be handled through that approach. Why? Because these two senders are there and they can be converted into a single source single group communication. Why? Because these two sources can send to the coordinator and coordinator in turn will send to one group. That also can be handled. Multiple sources and multiple groups is very difficult. It cannot be straight away implemented in triple SG way. So now we are going to see the implementation for multiple source and multiple group. One way to implement multiple source and multiple groups is through the propagation trees. So propagation trees for multicasting is going to basically solve the purpose. So let us see how the propagation trees are constructed. If this is the set of nodes, so we are forming the meta group out of these groups, and these meta groups can be organized in a form of a tree, and this is called a propagation tree. So in this example illustrating the propagation tree, meta groups are shown in the bold faces. These are all meta groups. So you can see that ABC is a primary meta group. So primary meta group will basically have group AB, AC, A, then B, and then C, and then BC also, and BCD also. So this particular ABC will become the primary meta group and becomes the root of all those meta groups. Now in turn BCD again will become the primary meta group for these meta groups, means BCD is here. So BCD will have BD, then CD, and BC is also absorbed, already absorbed in ABC, it will not be reflected over here, and D and DE. Now as far as the DE will become the primary meta group for E. So the meta groups for the primary meta group DE will be E, then CE and EF. Now EF will become the primary meta group for F. So just see that this complete groups of nodes, they are organized in a form of the propagation tree. Implementation of a propagation tree will now can be easily handled. So basically in this, once the propagation tree is there and you want to send the messages to a particular or in a multicast way. So first messages are sent to the primary meta group node, and that in turn will communicate to its meta groups, and if it has to reach to a meta group F, so it has to traverse through all the primary meta groups till that meta group which contains that primary meta group which contains that meta group reaches to that point. There it will be delivered in that particular tree fashion. Now there are various classification of application level multicast algorithms. So first there are 4 different class of multiclass algorithm. First one is called privilege based algorithm. In privilege based algorithm, the token rotates, so the node which is having the token will be allowed to send to the destination. So the process delivers message in the order of the sequence numbers. Typically the closed groups and causal order and total order will be there. There are 2 algorithms which are implemented based on this particular classification. Totem and on-demand multicast algorithms are available. The next one is called moving sequencer. So here there will be a sequencer, nodes are sending the messages to the sequencer. So sequencer's token has a sequence numbers and list of the messages for which the sequence number has been assigned. On receiving the token, the sequencer assigns the sequence number to the received but unsequenced messages and send the newly sequenced messages to the destination. Another next one is called a fixed sequencer. Fixed sequencer is like centralized approach that we have already seen. Centralized approach means there is a one single coordinator, and fifth one is called destination agreement. So in destination agreement, the ordering will be done among the destination. So destination receive the limited ordering information, and using time based Lampert's 3-phase algorithm, the agreement will be evolved. Few other algorithms for message ordering and group communication are available in the literatures that are listed over here. Conclusion: inter-process communication via message passing is at the core of any distributed system. In this lecture, we have discussed non-FIFO, FIFO, causal order, asynchronous order, synchronous communication paradigm for message ordering. Then examined several algorithms to implement these orderings. Group communication is an important aspect of communication in a distributed system. Causal and total order are the popular forms of ordering when doing the group multicasting and broadcasting. Then we have explained the propagation trees for multicast algorithm and classification of application level multicast algorithm. In the upcoming lectures, we will discuss about self-stabilization. Thank you.